Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology. Happy Friday to you all. I hope that everyone had a great week and is geared up for an excellent weekend. Before we get started, just for the sake of making sure that you all can hear me and make sure that my sound is coming through, before we start, I'd like you to give me a hypothetical or a virtual high five, if you will, if you can hear me, by clicking on the raise hand button on your GoToMeeting. So if you can hear me, please click on the raise hand button in your GoToMeeting, and that way I'll know people can hear me. I'm starting to see some high fives coming through. Thank you very much. High five to you all back. I've gotten plenty now, so I'll take it that everyone can hear me. Anyway, thank you very much for joining me today for our webinar on how to size and locate gas accumulators. And this webinar is being recorded. That way, if you are listening in live right now, you can certainly feel free to send the recording, which should be uploaded later today or early next week. You can send it around to your colleagues. You can listen to it again. Also, if you're listening in live, I've provided a copy of my presentation. That way you have it for reference for later. If you are listening to the recorded version, then please feel free to email me at benkeyser@aft.com, and I'll be happy to send you a copy of my presentation. That's benkeiser@aft.com. All right, I'm going to go ahead and get started here. Before we jump into the meat of the content, just a very quick overview on our various tools that we offer. If you're not familiar, we have AFT Fathom, which is for incompressible flow for liquid piping systems. There's 4 add-on modules: the goal seek and control, extended time simulation, settling slurries, all really useful tools. And I want to take a quick aside and talk about this one really quick here, the ANS module. The ANS module is a brand new add-on module for AFT Fathom. If you go to our website, this is what you're going to see, is this panel that pops up right over here. This is highlighting a very special promotion that we are doing for our brand new automated network sizing module for AFT Fathom. If you purchase before October 31st, you'll get 50% off the list price, which if you are in the United States, you can see our prices on our website. If you're outside the US, then please contact your channel partner and they'll be happy to get you that pricing. Now, here's what the ANS module is going to do for you, is it will help you automatically meet your design requirements by automatically changing your pipes in your system in order to minimize your life cycle cost or your piping weight or your initial cost. Very, very powerful capability. It's based upon the capabilities of AFT Mercury that have been around for 15, 20 years. And these capabilities are now integrated and streamlined directly into AFT Fathom as a new add-on module. So really easy to use. You don't have to learn a whole separate software. It's just an add-on module. If you go to the Learning Center under Webinars, followed by Webinar Library, you can access the previously recorded webinars in our library. Now, I thought that I had already filled out this information here, but it is making me fill it out again because I recently cleared out my cookies, and so I have to fill in this really quick because I want to show you something. There we go, that's good enough. All right, so if you go to our webinar library, there's a few webinars that are really useful for getting an idea of what the new ANS module does. So once you get here, go to AFT Fathom, and if you scroll down in the page a little bit here, there's a few webinars that relate. It's how to automate your pipe sizing calculations, how to utilize the automated network sizing module, and there should be another one in there. Those are 2 of them. I think it's called Size Your Pipes in No Time Flat, and apparently that one's not uploaded yet. We'll get it uploaded here soon. So anyway, those are some webinars that you can watch to learn about the ANS module. And then if you want to learn more about our additional products, just go to the products menu under AFT software overview, and this is where you can get all the information, high level basic stuff, and then click on any of the learn more buttons, and I'll take you right to that product page. All right, time to get into it. I'm going to skip past these next several bullet points here, and the AFT Aero ANS module will be available very soon. We're hoping in the next few weeks. We're just finishing up the documentation portion of that right now. Okay, so today's webinar is going to be a bit more advanced and focused on talking about gas accumulators. It's an excellent surge suppression device that you can have in your system to help you dampen out surges in your pipeline significantly. But there are some really useful AFT Impulse video tutorials on our website. And in the presentation, I have provided direct links to each of those videos for you. So make sure you go through and watch those. It will talk about how to section your pipes effectively. It talks about the different types of transients that you can model, how to use the various graphing capabilities. Those are really useful videos that you can watch. In addition, I also provided some direct links to previous Impulse webinars that we've done. And these are really helpful, especially the one on mitigating surge issues. In that one, I did talk about gas accumulators, but I also talked about other types of devices as well, like relief valves and vacuum breaker valves and surge tanks. In this webinar, I'm going to go into a lot more depth on gas accumulators specifically. Okay. So we're talking about surge suppression. Excessively high pressures can cause a lot of damage to your piping system. Your pipes can burst. It can damage pressure-sensitive equipment, and whenever you have a sudden pressure surge, you want to make sure that those don't cause problems. Low pressures can be just as bad, where you can have pipes that will collapse when your atmospheric pressures are above the internal piping pressure. So low pressures are just as an issue to avoid and prevent from happening as high pressures are, especially if your system pressure drops down to vapor pressure and starts to cavitate. There's two real big problems with cavitation. Inside the pipes, it's like balloons popping in your pipe over and over and over again, and that's not good. And then inside of cavitation inside of pumps, it's like little bubbles constantly popping on your impeller. So both of the things will wear out very quickly, and that's definitely something that you'll want to avoid. One thing I want to point out is that hang on one second. Excuse me, sorry about that. One thing I want to point out is that there's a theoretical equation that can calculate what the maximum theoretical surge pressure will be on a sudden transient event. It is possible where you can have higher than that maximum theoretical pressure, such as if you're cavitating or you have line packing, different things like that. So another thing to just be aware of when you're dealing with a water hammer situation. Not only are pressure surges bad, but they're going to cause imbalanced forces on your piping system, and those forces can move your pipes. They can break apart your supports or your insulation. There's videos that we showed our AFT Impulse training seminar where there's piping systems that shake and move several feet during a transient event. And they're pretty big pipes too, so it's definitely an issue that you need to avoid. And so there's several different ways that you can reduce these surges. One is simply reduce your operating velocity. The higher velocities that are in your system, the higher your pressure surge is going to be, because the pressure increase upon a surge event is directly proportional to the change in velocity. So reducing your initial steady state velocity is key to reducing pressure surges. Another thing that you can do is to slow the change in your operating conditions. When you're closing or opening your valves, make them do so in a very slower fashion. Don't just slam those valves shut. If you close them properly, then that's a great way of mitigating those surge problems that you might see. You can also change the profile on how equipment changes. So let's say that you have a valve closure, and this is CV versus time. A lot of times, if you don't know how the valve is going to close over a period of time, people will typically just assume a linear profile. Well, the linear profile can still cause a very large pressure surge, even if you make it close over a very long period of time. The reason why is because typically with these really long linear closures, the pressure surge, nothing really happens in your system until this point here. So as that valve is closing more and more and more, that's not causing any changes in your system values potentially. And then it's right at the end when that valve finally closes all the way, that's when things start to go haywire. So changing the way that the valve closes is key. So instead of doing a linear closure, there's an 80-20 rule where if it takes a certain amount of time to close a valve, well, instead of going linearly, close it 80% of the way in the first 20% of the time. And then over the remaining period, close it the rest of the way. So this is the 80-20 rule that I've talked about before, one of those previous webinars. Simply by doing this, that will significantly reduce your pressure surges in your system and can help you prevent having to buy expensive surge suppression equipment like relief valves and whatnot. All it really is just how you close your valve, not just how long it takes. And then finally, surge suppression equipment. There's gas accumulators, surge tanks, relief valves, vacuum breaker valves. Today, I'm focusing on gas accumulators. These are a couple of useful slides just for background information on code compliance. Piping codes like B31.3 for ASME and 31.4 talk about how to, they discuss handling surge pressures, and Impulse will help you quantify what those will be to make sure that you are compliant with those codes. So if you're not familiar with those codes, which I'm sure a lot of you are way more familiar than I am, be sure to check those out to make sure that you are staying within compliance there. All right. These are some really useful videos on gas accumulators, and I'm not going to play these right now. I want to, but just for the sake of time, I'm going to keep on moving forward. So I have provided direct links. These videos are excellent at really showing a good conceptual visual example of what's happening in your piping system if you have a sudden pump trip and you are dealing with a gas accumulator. You know what? I'm going to go ahead and play. I'm going to go ahead and play one of them. I'm going to play the second one right here after a pump trip, because that's the example that I'm going to be demonstrating today. So we'll go ahead and watch this. It's going to open up a web browser for me. Give me 1 second here.
Water and sewage pumping station.
Let me pause that. Turn up my volume. Okay.
As well as treatment plants are susceptible to the same surges in pressure when pumps operate or a loss of power occurs. With the bladder surge tank installed in a municipal water system, the pump startup partially fills the bladder surge tank with fresh water, while supplying the water to the long network of piping. When a pump shuts down with the bladder tank installed, gas pressure forces the water out of the tank, allowed the pipeline to flow continuously. The fluid stream, still without pump pressure, having dissipated its forward energy from the tank pressure, now reverses flow. The fluid energy now is forced into the pipe leading to the bladder tank. The fluid is directed up into the tank, dispersing through the floor plate so that the bladder can absorb the pressure evenly. The fluid now oscillates up and down in the tank as the fluid energy is absorbed and expended back into the pipe until the fluid returns to a static state.
Excellent. I love that video. It's really helpful for getting a good understanding of what's going on inside the gas accumulator and its impact on the system. So be sure to watch the other video when you have a chance, and that'll give you some more details there. Okay, so how do you model gas accumulators in AFT Impulse? They are simply pre-charged vessels with gas. You can have the gas will compress or expand inside the vessel to absorb your pressure surges. It will change the frequency response of the piping system. What that simply means is it'll change the overall, in a nutshell, the wave cycles for pressures. And it is possible that if you do not size and locate your gas accumulator properly, it could potentially cause more damage to your system than it would be helping. So you'll have to be careful on how you size and locate things. Some important parameters are the polytropic constant and the initial gas volume. That's typically what you need to specify a gas accumulator in AFT Impulse. You can also model a small flow restrictor. The flow restrictor can potentially help dampen out some of those pressure surges with changing the flow rate in and out of the tank. So that's another variable that you can control. You can also specify maximum and minimum volumes, which would simulate a bladder. That way it would prevent your gas volume from exceeding certain sizes. And this is the example that I'm going to demonstrate today. This is actually one of our standard examples. If you were to open up AFT Impulse, you would be able to find our example called Pump Trip with Accumulator, and it will teach you how to build a model of this piping system from scratch. The gas accumulator is pre-charged with half a cubic foot of air, and it affects the system response. Now, a couple of things. As I mentioned, this comes from our walkthrough tutorial in the examples help file. The example, it demonstrates how to model the gas accumulator. It doesn't teach you how to size and locate it. It does give you a little bit of a background on what we did to figure out exactly where this gas accumulator is supposed to go and how large it's supposed to be. That really is a bit of an iterative process, and the example does not take you through that. It pretty much gives you the final answer of exactly where that gas accumulator should be and the gas volume size inside the accumulator initially. So one other note is that I have modified the example file model to include an actual check valve junction. If you were to build the example from scratch, it has you specify a check valve inside of the pump itself, which is a modeling for convenience thing. I went ahead and actually modeled a physical check valve junction, and that way just gets a little bit closer to the reality that I wanted in my model here. So essentially, this is the final answer. So let me go ahead and open up this example here really quick. All right, so here's my system, and I want to take a look at the top system first. The top system represents my piping without the use of a gas accumulator. As you can see, my gas accumulator is placed right here, but there's this little X. What does that little tiny X mean? The X means that you have a special condition applied for that junction. So I have all my junction information filled out. I've got my polytropic constant, my initial gas volume. As you can see, I have placed my gas accumulator in line with the pipe, but that may not be the case. So instead of modeling an actual short connector pipe like this, you can instead lump that pipe within the gas accumulator itself. It's a little bit better because it still takes into account the momentum and the inertia of the fluid in the pipe, but it's not going to change your pipe sectioning. If you were to put a little short connector pipe right there, then that's going to throw off your pipe sectioning and potentially cause you very long run times, which are completely unnecessary. So I have all of my input specified here, but if I go to the optional tab, you'll see that I have the special condition applied to ignore the accumulator. This is a very convenient option because I can still place the junction there, but when you go to the optional tab and apply the special condition, it allows you to ignore it and pretend that it's not even there. That way you don't have to go in and delete all of the information that you've already specified on the gas accumulator model tab. You can keep all that information there and just ignore it. So what this will do is it causes it to act just like a branch junction. It's doing absolutely nothing but connecting these two pipes right here. That's all it's doing in my upper system. So the reason why I did that is because the transient that is happening is I am running a pump trip example. So here's my pump, and it's operating on its curve, and I'm tripping the pump from the beginning of a transient simulation. And it is possible that there could be a little bit of backflow through the pump. That's why I'm using a 4-quadrant data set for my pump. And then I've got my check valve right here that can be set to open and close based upon different conditions. So this is the system that I wanted to specify and simulate what the effects will be if I do not have a gas accumulator that is working. The bottom system does. In the bottom system, there's no X in front of that label. And so as you can see from the optional tab, I am using the gas accumulator in the bottom system. So this will absorb and dampen out those pressure surges accordingly. One other note here is I've already created a couple of groups. Creating groups is a really useful thing to do because it allows you to plot two things together. If I wanted to compare the pressure profile along this flow path with the pressure profile of this flow path, you can do that by creating groups. So what you would do is select one flow path first, go to the edit menu, click on groups, and then go to create. After you give it a name, you'll see that name appear here in the system. And so I have my group called with accumulator, and that is going to be using these pipes right here. So when you have multiple groups like that, the multiple groups are what allows you to compare different flow paths. Now I've already ran the model and I already have results. So if I go to the output window, I can take a look at the results and get a feel for what's going on. So if we look at the maximum and minimum values, here's the maximum pressures for the system without a gas accumulator. And as you can see, the maximum pressure gets up to be almost 300 psia. Versus if I use a gas accumulator, words are hard for me today, I guess, then you can see here that it significantly reduces the maximum pressure that you'll see in your system. So that's good news. Now, one thing that I did was I created some design alerts myself, for myself. I went to the tools menu and then design alerts, and I have two of them. One is I want to make sure that my pressure is above atmospheric pressure for all the pipes. And then two is I want to make sure that the pressure is below 175 psia. That's the maximum pressure that I want to stay within. So when you specify those design alerts, what happens is in the results, if any of those design alerts are violated, you'll be notified with these messages here. And then if I add on the static pressure to my results here, so if I add in static pressure, it will highlight those violations in the table as well in yellow. So as you can see, I'm violating my maximum and minimum pressures just about everywhere. Excuse me. All right. So let's take a look at the event messages. You can see from the event messages that the two pumps tripped at the very beginning of the simulation, which is what they're supposed to do. But then I have a significant amount of check valve chatter. So let's take a look at what's going on with that. If I go back to the workspace, what I can do is I can right click on my check valve and I can generate a transient junction graph from the workspace. Let's look at the CV profile. So if we take a look at the CV profile for the check valve, you'll see that there's some oscillation there. And look at this. The check valve stays open until I get reverse flow, and then bam, it closes. And then it starts to open up again, and so it chatters for a little bit amount of time there. Well, what does the pressure look like in that instance? If I right click on the same check valve on the workspace, I can now generate a transient graph for the upstream and downstream connected pipes. So this is inlet and outlet of the junction. So let's plot the static pressure and see what's going on there. Well, look at that. That is some massively large pressure spikes that we're seeing there. Let's break this down a little bit. Let's take a look at this graph first. The static pressure at the outlet of pipe 2, this is the upstream side of the check valve that we're looking at right here. So that's the red line. As you can see here, when we go back to the graph, when that check valve, or when the pump trips, we have the system dropping in pressure, and then there's significant oscillation going on between the upstream side of the check valve all the way back to the supply reservoir. That's not so bad. The other graph is a lot more violent. So as you can see, when we have that drop in pressure from the pump trip, our check valve opens because the velocity reverses. And then once that check valve closes, here's our initial pressure spike for that check valve closure. And then we have an even higher pressure a little bit later. The reason for this is because we have some pressure waves that are superimposing on each other and causing a higher amplitude in that second spike. And then, as you can see here, it takes several seconds. This simulation goes for 30 seconds, and those pressure waves are still not even dampened out in that amount of time. And so that could oscillate for quite a while when we don't have a check valve in place. So this goes way above my design alert. My design alert is 175 psia as well as atmospheric pressure. So this is a major issue. Now, one of the things with regard to water hammer modeling is you cannot just look at one specific area of your model and be done. It's really important to pay attention to what's going on throughout the entire system because of the way that the pressure and velocity waves interact with each other. Excuse me, I had to mute myself there for a quick second. So after you would look at specific points like this, maybe you also want to see what the pump trip looks like. Well, if I right click, I can do my pump speed graph here, and you can see how the pump speed drops off over time. But what we want to see is a animation. So this is where I'm going to create a animation, and I've already done that. So here's my pressure profile with an animation, and I'm showing a lot of stuff here. What I did in order to create this graph list item, this is my graph list manager, and I've got a couple of graph folders, And then I have multiple graphs in the particular folder that I'm looking at here. The reason why that's really useful is because when I want to come and do a webinar and I don't want to rerun the model, I don't want to reset these parameters every single time, all I needed to do was double click on this graph list item and that reloads it on the spot. It's beautiful. One of the most powerful features. And so what I did was I already specified the parameters here in this graph control section. So what I'm showing is the profile that does not use a gas accumulator. I'm showing the pressure as well as the elevation. With the elevation, I clicked on a button right here, which indented the elevation. That gives me my secondary y-axis over here. And then after that, I am showing the maximum and minimum pressures. I'm showing the initial steady state values, and I'm showing my design alerts with my animation. So there's a lot of stuff going on there. So now on the graph, here's what we have going on. The dark dotted blue line at the very bottom here, that's our minimum pressure. That's vapor pressure. You're going to see very quickly how fast the system pressure drops to vapor pressure. The green line here is my initial steady state pressure. So initially in steady state, my pump is boosting up the pressure, and then this is my pressure loss as I go throughout the rest of the profile there. So that's what the green line represents. The lighter dotted blue line here is my atmospheric pressure design alert. That's my minimum pressure that I want to stay above, my design alert. And then I've got my maximum pressure design alert of 175 psia here. Then you can see this dotted red line, that's my maximum pressure in the system. And then right now it's covered up by the green line, but that's going to be our animation here that we're going to see in just a sec. So when I click on the play button, you can see how the pump trips. So as I pause this new red line that you see, this is actually the transient pressure all throughout the entire system through the profile. This is why using Impulse is really helpful, is because you can do these types of animations to see what's going on all throughout your network. So my pump is tripped and my pressure is dropping, and you see how it's dropping throughout the entire flow path of the whole system. Now, at this point, this is where I have finally started to drop below atmospheric pressure. I'm not cavitating yet, but I'm below atmospheric pressure. That could be a problem, especially if you have a requirement that your pressures have to stay above atmospheric and you're not allowed to have a vacuum in there. So we'll keep on playing this. The system pressure begins to drop. What's happening there is that pressure wave, it's reflecting back up to the supply end of the system. So when this pump is tripped, that trip has to communicate itself all the way down the line. And then once the end part of the system realizes that the pressure has dropped, it has to communicate back to the source, basically telling the upstream side, yes, I see that we have a decrease in pressure now. So I keep playing the animation here, and then we have some oscillation. Now I'm going to speed forward the animation just a little bit until some more excitement starts happening. Right now, not too much is going on because right now the system is just oscillating between slightly sub-atmospheric pressure and a little bit above atmospheric pressure. But at some point, we're going to see that check valve close right now. So here's the check valve right there. Watch how the pressure here goes way up high, and watch what that does to our system. Now I'm going to go back to default speed. So our check valve closes. That pressure rises incredibly quick. Not even a second to go all the way back up. It's a few milliseconds where it increases very, very rapidly. And then look how the whole entire system pressure sees that large pressure surge as well. Now it's going to reflect, and watch how the system pressure drops again. It's going to drop, and then once that pressure wave gets back to the check valve, it's then going to reflect negatively. So watch what happens here as I move forward time step by time step. In one time step to the next, it's dropping all the way down to vapor pressure, not at the check valve though yet. It's starting to drop down to vapor pressure later on in the pipeline, right around in here. So that's where I'm going to see my first bubbles starting to form in the system when I begin to cavitate. So now look at how widespread this cavitation is. It is very significant. It goes on for several hundred feet. And now that everything's at vapor pressure, those vapor bubbles start popping, and we start to see a lot more chaotic results and violence in the system. The first few pressure spikes that happened when one of the first bubbles started to pop will be the most reliable pressure spikes. But as we continue to play the animation and we see all of this madness going on, this may or may not be realistic responses in the results. This is very hard to predict what's actually going on in reality. The reason why is because in reality, when you start to have cavitation, the wave speed of your fluid actually changes. But in impulse, it's assuming a constant wave speed. So these results may or may not be realistic. That's where it's really important to watch my cavitation webinar that I did a while back. Again, there's a direct link in today's presentation to where you can find that webinar. And so it requires a very careful eye to examine how that cavitation is affecting the system. So this is our system without using a gas accumulator. I've got major problems. I've got cavitation, but in addition to that, I simply want to make sure that my overall pressure is just staying between these limits. Here's my maximum pressure design alert, 175 psia, and here's my minimum design alert, atmospheric pressure. So now we're going to consider the system that has a gas accumulator in it. So that's this system down here. Now, that check valve is J103. If we looked at the event messages, we would see some chatter. I can also right-click on the graph here, or on the visual report on the check valve, and let's see what kind of chatter is going on for this check valve. As you can see, hardly anything, just a very tiny little bit. So once we get a very little bit of reverse flow, that's when that check valve closes. And if I click on this, let me circle it for you. This button right here, it opens up our rangefinder. The rangefinder is a really, really useful tool because I can drag the ends of this and zoom way in, and that way I can look into different areas on the x-axis and I can see how significantly that check valve is chattering. As you can see, not very much at all. So that gas accumulator is absorbing pressure waves. So let's take a look at the gas accumulator. I've already created a graph for the gas accumulator. I could look at the pressure and volume. I already created that, so I'm just going to go ahead and load it for you. Well, I thought I did. So I'm going to go ahead and just do it right here. So we've got our gas accumulator. That one's not the one that works. This one does. And so I want to show the volume as well as the pressure. So here, this is where you can see how the gas accumulator is absorbing the pressure surges over time. So this is doing a really good job of dampening out those waves. And let's take a look at the animation now. So I'm going to close out some of these other graphs here. And I'm going to open up my pressure profile with animation for the gas accumulator. So as you can see, I've plotted the same exact things, but for the bottom system. All right, so I'm going to go ahead and speed up the animation a little bit, and we'll play this. Well, I'll slow down again. So we have our drop in pressure. Look at what's going on. Immediately, when that pump starts to trip, this gas accumulator is starting to help out with maintaining that pressure to where it's not dropping so incredibly quick. So it's doing a really good job at absorbing this pressure surge. So our system drops, as you can see by the dark blue dotted line right here. The only place where it gets close to atmospheric pressure is right here in this area near the end of the pipeline. That may be manageable. And then the only area where the system pressure is above my design alert is in this area. The question is, when my system pressure starts to increase to get up to this maximum value, when does it do that and how long is it sustained? If it's just a fraction of a second, maybe my pipeline can withstand this maximum pressure. So you just have to keep looking at your animation to see what's going to happen. So now I'm starting to see some oscillations because my check valve is closed. And in time, the system pressure is going to begin to increase again with the fundamental nature of water hammer, with how those pressure waves pass back and forth throughout the system. But the beautiful thing about using the gas accumulator is that this pressure increase is much, much slower than it is without the gas accumulator. So here, this is where we're going to be getting above that maximum design alert. So it comes up and it touches it. Look, it was just after 6 seconds. So that pressure gets to be higher than my design alert, and that part of the system, not even more than a second. Now, if I pause this and I march forward in time by grabbing the scaling tool, we can see here that it does not exceed that maximum design alert again. It stays well within my minimum and maximum design alert conditions. So look at that. The gas accumulator is doing a phenomenal job at damping out those pressure waves, and this is much more manageable and it's not going to damage your system. So this is what the example walks you through on how to model the gas accumulator. This brings up my next question. Where should we put the accumulator and how much gas should there be inside? Well, it's a very iterative process to figure that out. And so there are several things that will affect your how well your gas accumulator responds with your system in order to try and dampen out those pressure surges. So there are several factors. How close your gas accumulator is to the source of the transient. You want to try and put your gas accumulator as close to whatever is causing a transient as you can. If it's a pump trip, put it as close as you can to the pump. If it's a sudden valve closure, put it as close as you can to the valve. Now, sometimes you might have various restraints that might not allow you to put it exactly that close to your source of the transient. So the proximity of your gas accumulator, that could be potentially a variable for the location. Your initial gas volumes and different types of gas are also variables. So that's what's going to dampen out the accumulator and its performance. So if you add a 0.1 cubic feet of gas inside the accumulator versus 1 cubic feet, that's going to have a completely different effect on how the accumulator will perform. Other variables include your connector pipe and size. So if you go back to the model that I had right here, I put the pipe in line with or I put the accumulator in line. So one of the variables that you can play with inside the accumulator is this short connector pipe. You can change the diameter, the length, and that will also have an effect on your gas accumulator response with your system. So there are a lot of useful capabilities in AFT Impulse that will quickly help you be able to figure out how to size and locate your gas accumulator. Pipe splitting, special conditions, global editing, duplicate special, importing Excel changes, also exporting Excel results can help. Design alerts, creating groups and graphs. Get creative. There's a lot of incredibly useful features that will help you very quickly go in and figure out where that accumulator should be. So when I go in here and I'm trying to figure out what should my pipe lengths be and how large should my gas accumulator should be, don't do it in just one scenario. Here's an example of how I did this. Just let me get to the next slide. So here I have several systems. So what I did was I took that original system right here and I stretched it out and I put several gas accumulators in line. And what I did was for all of the gas accumulators except for one of them, I applied the special condition to ignore them. So in this very top system, I am only accounting for the gas accumulator right here. So this is closer to the pump trip. And then I took this system and duplicated it, and then I did this one, and then this one, and then this one. And so there's a lot of ways that you can speed this up. The next thing that I did was I created different scenarios. In one scenario, I used a certain gas volume, and then in other scenarios, I changed the gas volume with a quick global edit. So here's how you can very quickly set up over 30 different scenarios, which can help you very quickly size and locate your accumulator, making you very, very efficient with the software. Now, I'm not going to do all 30 in today's demonstration. I'm going to do just a few of them. So here's what I'm going to do, is I'm going to save this model. Sizing and locating. All right, so here's what we're going to do, is I'm going to get rid of this system here because we know that we need an accumulator. I don't need to have a system on there that is representing no accumulator. So here's what we're going to do, is I'm going to turn on my grid. That's from the arrange menu. And then I'm going to take my reservoir and I'm going to move it way out over here. So as we can see, if we look at the pipe lengths, we have 10 feet between the pump and the check valve. And then we have 40 feet between the check valve and the accumulator. And then we have 940 feet between the accumulator and the discharge tank. The key thing is we know the answer of where this accumulator should be. But the situation is maybe we don't. So what we're going to do is I'm going to start off with putting this at 25 feet. And this is going to be my first location guess. So I'm guessing that this first gas accumulator is going to be 25 feet after the check valve. Now I need to go in and re-update my downstream pipe because this is actually 1,000 feet. And here's what we're going to do. We're going to split that pipe multiple times. So here's how you split the pipe, is if you hold the shift key down, you can hover over any of these junctions, and then while hovering over your junction and holding the shift key, click on that junction, drag and drop the junction onto the pipe, and it's going to bring up our pipe splitting window. This is where you can dictate where your pipe or where your pipe is going to be split. So I want this to be split 25 feet after the first heat exchanger. Now, as you can see, I have a little ampersand in front of the pipe. That means that in this 1,000-foot long pipe, I've got several fittings and losses lumped into that pipe right there. I don't want those to be on pipe A. I'm going to move them over to pipe B. So I move them over to pipe B and I click OK. And now I've got my second gas accumulator. I'm going to stretch things out a little bit more. So I'm going to put this guy right here like this. And then I'm going to split the pipe again. So I'm going to hold the shift key down. I'm going to split the pipe. I'm going to, again, put this 25 feet downstream, move the fittings onto the next pipe, move that down a little bit, and then I'm going to split it one more time. I'm only going to do 4 accumulators, so not as extensive as my other actual model, just for the sake of time. Now I'm going to collapse the quick access panel to give myself a little bit more real estate. I'm going to make my font size a little bit larger. So I'm going to go in here to colors and fonts. I'm going to make it size 16. That way we can see it. And I'm going to name my junctions. So this is going to be called GAA. And that stands for Gas Accumulator A. And this will be GAB. And then we have GAC. And then finally, GAD. Now, if you have a system that looks like this and you want to apply those names, it's actually really super easy to do than what I was doing. If you were to open up a file explorer on your computer and you were to browse where AFT Impulse is installed, as long as you're using AFT Impulse 7, this will work with our new Excel import workbook. So if you go to Impulse 7's application folder, here's this beautiful template for Excel changes that we've created for you. So if you open this up, this is where you can update massive amounts of data all in one shot. You can do it for multiple scenarios as well. There we go. So here we've provided this template for you. So if I do another row here, I can choose gas accumulator. Look at all the different parameters that I can change. I can do the junction name. So instead of doing the name changes on the workspace, I can put all my junction names in the spreadsheet and then import those all at once. So it makes you very quick and efficient. You can also do this for the initial gas volume, polytropic constant, special conditions, etc. And so that way, when you start going through the model, you can see here how some of these are missing information. They don't have the polytropic constant or the initial gas volume. No problem there, because I'm going to do a very quick global edit. I actually want my gas accumulators to all be at 0-foot elevation. When I did my pipe splitting, it automatically figures out what the elevation should be when you split the pipe. But I want them all to be at 0. So I'm going to go to Edit, Global Junction Edit, and I'm going to edit my gas accumulators. So here's what we're going to do. I'm going to select all because I'm going to change all accumulators. They're all going to have an elevation of 0. They're all going to have a polytropic constant of 1.2. And I'm going to start off with a gas accumulator volume of 0.25. Excuse me. Now, something to pay attention here is when you're doing global editing, this is a template window. So even though these items are blue, meaning that they're required input, if I don't care about specifying the initial gas volume, I could leave it blank if I like. But something to notice, the name here is called gas accumulator. So when I go to the next step of clicking OK, this is the list of changes that I want to change. I have to be very careful to make sure I don't just willy-nilly click on all, because what that will do is it will change the names of the gas accumulator. So with great power comes great responsibility. Be careful when you're doing global editing. So the only things I care about changing are these three parameters: elevation, polytropic constant, and initial volume. I'm going to apply the selections. I'm going to also renumber my system because it's kind of skewed. So I'm going to click on edit, and I'm going to go to my renumber wizard. And I'm going to number these from left to right. So 1, 2, 3, 4, 5, 6, 7, and then 8. And I'm going to do the same thing for the pipes. Now, this is not something that you have to do. This is just something that I like to do because the numbering makes sense. So once your system is built, you can go in and renumber things to a way that makes sense. All right. So I've got my system. What's not defined? Everything's defined. I just have to go in and resection my pipes and then go into the transient control, and the only thing I need to do is just click OK. And so now what I'm going to do is I'm going to take these three gas accumulators. I'm going to apply the special condition. In addition to going to the optional tab, this button right here also applies special conditions. So I'll click on that. And then what I'm going to do is I'm going to zoom out, and I'm going to select that entire system, and I'm going to do a duplicate special. Edit, duplicate special, and I'm going to offset the numbers. That way I can see that pipe 1 corresponds with pipe 101. I'm going to paste it right there. I'm going to duplicate special 2 more times. So I'm going to put this right there, and then click paste, and one last time. Duplicate special. That paste preview mode is really nice. That way you can put things right where you want. All right, so here's where I'm going to update the special condition. This time, this one is going to be off, and this one is going to be on. And then this one is going to be off, and gas accumulator C is going to be turned on. And then gas accumulator D is turned on, while gas accumulator A is turned off. So right now I have 4 different systems where I'm trying 4 different locations. This is all of a single gas accumulator volume, which is 1/4 of a cubic foot. So here's where things get a little bit more fancy. I do have to go in and resection things. Doesn't take long. So here's where I'm going to use some scenarios. I'm going to try 3 different gas volumes. So I'm going to call a scenario called initial gas volumes. And then I'm going to call it 1/4 foot cubed. And I'm going to create 2 other children. I'm going to do 1/2 foot cubed and 1 foot cubed. Lastly, I need to set up my design alerts. So I go to Tools and then Design Alerts. Actually, they're already set up, so that's great. I just need to update them for specific pipes. So this is going to apply to all 28 pipes. That's good. And I want this to apply to all 28 pipes as well. All right, now I just need to go into the different scenarios and change the gas volume. So I can double click on my 1/2 cubic foot scenario, go to Edit, Global Junction Edit, and then Gas Accumulator. The only thing that I'm changing is the gas volume, 1/2 cubic foot. Click OK. This is the only box I'm checking, and I'm done. And then the next thing is the 1 cubic foot. So in the 1 cubic foot scenario, same thing. I just go in here and I do all, and I'm going to set all the accumulators to be 1 cubic foot, only checking the box for the initial gas volume. And as you can see here, when I created those different scenarios, it remembered the names, it remembered which specific gas accumulator is in operation. All that information is preserved. So now I have 3 scenarios. And what I could then do is do a batch run. So I can go to File and then Start Batch Run. And this is where I'll be running each of these different scenarios one after another. Now, that's all there is to it. You would simply go in and try placing those gas accumulators in different spots throughout your system. And then you would try doing different gas volumes. Maybe you might try doing some different restriction sizes or perhaps different connections if you have short connector pipes in there. All of those are different things that you can play with when you're trying to size and locate your gas accumulator. And then I'm actually going to go ahead and cancel that. And I'm going to open up the one where I had all 30 scenarios, because that one actually has results. So that way it'll give you a flavor for what it's doing. So here's sizing and locating. Okay, so this is the overkill scenario, or the overkill model, where I did 30 scenarios. The scenario that I'm looking at right now is the 1 cubic foot. We'll start off with 0.1 cubic feet. So if I did 0.1 cubic feet, one thing I already did was I already created my groups. So if I go to groups and then manager, I did several groups of these different paths. That way I can plot everything together. So now if I go to my graph results window, what we see here is the maximum profiles with design alerts. So look at this. This is the 0.1 cubic foot scenario. If I hide the legend by right-clicking on my graph, you can see how pretty much everything violates the design alerts. Just about everything drops below atmospheric pressure on the downstream end of the system, but on the upstream end of the system, several areas drop below atmospheric pressure, but not everywhere. Maybe these 2 systems right here, those are areas where the gas accumulator was closer to the pump. So the closer to the pump, the better it prevents your upstream end of the system going below atmospheric. But look at this. This is a major problem, and I don't want that. So this immediately tells me that the 0.1 cubic foot system is not going to work. I also went ahead and created some force graphs. This is what the forces look like for each of those legs. Basically what I did was I created a force set from the check valve up to the last accumulator before it starts going uphill. And so this is what shows me the forces of that check valve when it slams shut. When that check valve slams shut, all that fluid momentum drops to the downstream end of the upstream end of the pipe, and I have really large forces here, and that's what we want to avoid. So as we can see here, the 0.1 cubic foot scenario is not going to do it. Let's look at 1 cubic foot. 1 cubic foot is much better. So if I go to the 1 cubic foot scenario and I plot my design alerts with maximum and minimum pressure profiles, look at this. It's beautiful. No matter where I put any of my gas accumulators, they are all below the maximum pressure design alert and are all above the minimum pressure alert of atmospheric pressure. So really, I know that I'm going to go with 1 cubic foot because that does a really good job at dampening out those pressures. But the next question is, how do I figure out where should I put my? Well, the question of where I should put my accumulator is going to be dependent upon the spacing. So this is where I start looking at things in a little bit more depth. So if I go to my graph results, let's take a look at the forces for this. Here are the transient forces that result when that check valve slams shut downstream of the pump. And I'm going to hide several of these force graphs. So here's the transient force response, where you can export this data into a pipe stress software, and you can do a pipe stress analysis. This is what happens when you put the gas accumulator really close to the pump, the source of the transient. So this does a good job at really dampening out those pressure waves. Now, if I go on and add the next force set, you can see how the spikes of the initial force right here gets to be a little bit larger. And then let's add on the next one. It gets to be sooner and larger. The green one is a lot larger. If I go to the graph where I put my gas accumulator all at the very end here, after a couple hundred feet, really far away from the pump, then I'm going to have a really high force set. So this tells me that based upon the forces, you could also look at pressure animations and other things like that. But this tells me I'm going to need 1 cubic foot of gas, and the best place for me to put my gas accumulator is as close to the pump as possible, which in the case of this model right here is going to be 25 feet plus 10 feet. So 35 feet away. Actually, that's this system right here. This is where my gas accumulator needs to go. So the features that I showed you here with the duplication, the pipe splitting, the global editing, the scenario manager, and the different graphs, and the design alerts, those are excellent capabilities that will help you very quickly go in and figure exactly where your gas accumulator should be. And this is exactly what we did basically to figure out the final answer that I demonstrated for you in the first part of the example. And this whole iteration process was left out of the tutorial process. All right. Well, that is basically all there is to it when you want to size and locate gas accumulators. Again, if you go to the help menu under show examples, this is where you can find all of our example tutorials, which showed up on my other screen. Let me pull it over. So basically, the example that I talked about today is pump trip with accumulator. Now, if you download and install AFT Impulse 7, if you don't have a license available, you could still open up the help file directly. There's another one called positive displacement pump. This is a really good example where it simulates a duplex pump and a triplex pump, which are modeled as positive displacement pumps. And what we try to do is figure out what the response is going to look like with no accumulator here versus if we put a gas accumulator there. And you can see how the response changes significantly when you have a gas accumulator in place. So this is the pressure response at the pump discharge for the duplex pump with no accumulator. This is the triplex case with no accumulator. So the triplex pump still smooths things out a little bit, but there's a significant amount of oscillation. So that's where it's very, very helpful to put a gas accumulator not only to dampen out surges like upon our pump trip, but the gas accumulators are also extremely helpful for mitigating pulsation issues. And so this is the duplex pump with a accumulator, and this is a triplex pump with an accumulator. And so that's definitely the way that you want to be able to model those. And if you were to use a gas accumulator in the duplex and triplex pumps, look at how this dampens out the pressure at the accumulator. It's very small oscillations there. So this is another example that you can explore. Again, simply download and install AFT Impulse 7, and then you can go on your computer and then browse to where it's installed. which is typically going to be on the C drive. And then if you go to the examples folder, here's the other place where you can find that examples help file. And that'll teach you how to build both of the models from scratch. Well, everyone, thank you very much for your time today. That's all I have. If any of you have questions, or if you want to try out AFT Impulse, if you don't already have it, then don't hesitate to reach out to us. You can feel free to email me at benkeyser@aft.com, or you can email sales@aft.com. And then for tech support, you can email support@aft.com, and our team of applications engineers will do a phenomenal job at helping you out. Thank you all very much for your time today. Take care and have a wonderful weekend.